Okay, let's do this next section. Let's make something already that you'll be happy about. This next section is, wow, there should not be a comma there. The next section is complements, conditional probability, and Bayes theorem. Right? Ready? Everyone is going to be very happy about this. We are not going to do Bayes theorem. I actually think Bayes theorem is really cool. There's a whole field called Bayesian analysis, but this textbook gives like a half a page to it. And I think I've taught Bayes theorem to business students before, and it usually takes about 2 class periods. It's too involved, and the book does not give it enough support. So I am just not going to teach it to you, and you should be okay with that. Now, complements we already know. Emma, was that you that gave me the 1 minus? Who was the one that told me this? Did this at the beginning of class with the bar? All right, no, maybe that was Gina. Okay, so complements. Everybody remember, complement is an event not occurring, or it's the opposite of an event, right? So the probability of a complement, right? If it rains sometimes tomorrow is an event, then the complement of the event would be that it doesn't rain anytime tomorrow, right, etc. So we're going to actually calculate conditional probabilities. We're going to use conditional probability notation. You've already done that. You'll describe one, already done that a little bit, and you'll use complements of an event to calculate probabilities. We're going to start with the complements. So you might have questions, right, that are like, I randomly select 100 Americans. What's the probability that at least one of those folks has been to Mexico or been to France, something like that, right? The complement of at least one is none. We follow with that, right? So one minus the probability. So let's say I select 100 people, right? The probability that one or more been to, I don't know, wherever. One minus that's the probability that none have been. Or vice versa. The probability that none, actually, this is easier. The probability that at least one, like, let's say I select 10 people, right? The probability that at least one of them has been to Mexico is going to be 1 minus the probability that none of them have been to Mexico. Are we following what I'm saying? It turns out that sometimes this event is much easier, right? Remember, I did an example of this. I said we wanted to figure out what the probability of getting 10 or less on 2 dice. Was easier to calculate the probability of getting more than 10, right? Because that was only 11 or 12. This is the same thing. So let's do an example. Hopefully I read this correctly. I remember I read this next example incorrectly. There's a study, right? I've seen lots of students in my time with damaged phones, etc., right? Of damaged iPads, 6% of iPads were damaged by bags or backpacks, right? So let's say I randomly choose 20 damaged iPods, right? iPads. No one has an iPod anymore. I'm old. Okay, so what's the probability at least one was damaged in a backpack? Right now, this probability would be difficult to calculate directly because it turns out you have to calculate things exactly, right? So is it different if I want to calculate so let me just say that read this as probability of one or more iPads is damaged by a bag or backpack, all right? I can kind of do what I did there, but I would have to know the probability of exactly one iPad being damaged plus the probability of 2 plus the probability of 3 all the way up to all the iPads being damaged in that manner. As you can guess, that would take a long time and be very difficult. It's much easier, right? Did you guys see that, right? If I say at least one of the iPads is damaged by backpacks, right? That means 1 is damaged, exactly 1, exactly 2, exactly 3, all the way up to 20. Those all fit in that, right? So if I wanted to calculate this, I would need to add 20 different probabilities together. It's much easier to calculate the probability that none of the iPads were damaged by backpacks and subtract that from 1. Are we all following what I'm saying here, right? Sometimes an event, it's easier to calculate. Okay, so I have 20 damaged iPods, right? So let's try to look at this. Let's assume, so I'm going to assume that each of these are independent events, right? So I wrote all work because I was thinking about what it meant. So we're trying to figure out the probability that none of them were damaged by bags, right? Okay, so let's do this. If 6% were damaged by book bags, what percent are not damaged by book bags, everybody?
94.
94, right? So the probability that it's not damaged by a book bag is 94%, right? But let's say I have 20 iPads, right? Well, each iPad being damaged by a backpack, those are independent events, right? So the probability that my first is not damaged, this will give me the probability that my first 2 are not damaged, right? This would be the third. How many times would I need to do this? Why 6? 6% are damaged, but how many iPads do I got here? 20. So I'm multiplying 20 times. But what's a more convenient way to express that? Yes. So it's 1 minus. I can multiply like this because each event's independent, right? Yeah.
How did you get?
Plug down your calculator. 9.94 to the 20th power. I have these numbers, Regina, written down ahead of time, so I don't have to plug them in the calculator every time I teach this lesson. So yeah, no magic being done there. Let's do a similar one. Okay, so I roll 5 dice. What's the probability of getting at least 1 5? This is difficult to calculate because I need to figure out the probability of getting exactly 1 5, 2 5s, 3 5s, all the way up to 5 5s, right? But I can much easily find this by doing 1 minus the probability of what? Say that again? Of getting no 5s, right? Let's be clear, no fives on the 5 dice, right? I'm rolling 5 dice. Want to know what's the probability that at least one of them is a 5, right? What's the probability of not getting a 5 on a single roll? This is easy. I roll a single dice. What's the probability I do not get a 5? 5 out of 6. We all good with this? How many different times am I rolling a dice? Yeah, 5 dice. Yeah, I'm rolling 5 times, right? Or one, right. And are each of those rolls independent? So I can simply multiply them and each has the same probability. So a faster way to multiply would be to write this as 5, 6 to the 5th power. You type that into your calculator, you will get approximately 59.8%. Be careful how you write that in though. You'd want to write 1 minus parentheses 5 divided by 6 caret 5. You need to put parentheses around this because otherwise it will do PEMDAS, which means it will take the 6 to the 5th before doing the rest of the calculation. You want to take the entire fraction to the 5th power. Questions on this? Yes, Bobby.
For the last part, is that a percent or is that the?
That's a percent. I converted from a decimal to a percent just to give you. Your calculator would obviously give you a decimal, right? And then you can make it into a percent. If you wanted to. Sure, just to make it simple, I'll just say that it's. All right. Let's now, that was the complement part of the lesson. Let's focus on the important part. Conditional probability, right? So conditional probability, I told you, is the probability that one event occurs given that another event occurs. So we are going to try to figure out, so here's a Venn diagram, right? So I'm going to be talking about Mattoon, right? Which is where I used to work. I made up these numbers for that and I never changed it to Chicago. Or Alsip, which is where I live. Okay, so let's just kind of put the number of days, right? Read this. So it rains an average of 112 days a year in Mattoon. It also averages 180 cloudy days and 90 cloudy rainy days. Let A be the event that it rains and B be the event cloudy, right? So let's look at this diagram. What number, this 90 days that are both cloudy and rainy, where does that 90 go? You should know this. Where do I write that number? Crosses. Okay, yes. Now, it says that it rains an average of 112 days a year. Should I put 112 here? Classmates, should I put 112 where I put it? The answer is no. Why not? Those 112 days, what are those days? What does that include? Yes, that's right. So what Mars is saying is these are what? No. So these 112 days include these 90 days where it's both, right? So I should do 112, 90, right? And that I don't know why I wrote 99, right? And I will get 22. So there are 22 days where it only rains. We following how I got that number? And then there are, yeah, so then I should do 180 minus 90 because there are 180 cloudy days and there are 90 days that it's both to get the number of days that are in B without also being in A. So let's then, class, we can easily fill this rest of this diagram out together. What's the probability of A? So A is the event that it rains. So how many, so we just can look at sample space stuff, right? What is the number of outcomes in a sample space, considering that we're looking at days in a year? 365, let's just forget about leap year for the time being, just keep this simple. All right, and how many of those days does it rain? Not 22. 112, because, right, raining should also include the days that it's cloudy and raining, right? As a decimal, this is approximately 0.31 or 31%. So this is a very rainy. I made these numbers up. This sounds way more rainy than any place I know. It rains about 31% of the time, okay? Same idea for B is, so B, probability of B. The probability it's cloudy is what out of what? 180 out of 365. Same thing. I don't want to circle percentages. It's actually the decimals that are the best here, but you can other way the percentages, you can mentally translate them. Okay, now this is a little, now this one's not hard. What's the probability of A and B, that it's both rainy and cloudy? 90 divided by 365, which has a decimal. Yeah, and this is just me getting it. That's the same place where I got that number earlier, Regina, right? I just previously did a calculation. Okay, here's the harder one. What is A given B? All right, so let's just think about this. Event A is that it rains. Event B is that it's cloudy. So it's rain. This, I can read this as rains if cloudy, right? If it is cloudy, I know it's cloudy. So that changes the size of my universe, of my sample space, right? Because I know, what do I know about the days for part E? I know that it is, I do, that is how many days there are in the year. But what does E say? This says rainy if cloudy. So what do I know about that day? About the story in E? It's out of 180. Why? Yeah, so the denominator changes. Let me think about this, right? We know B has occurred, right? So that means I must be living in this yellow circle, right? We're kind of following, class, right? So that changes the number in the denominator for the first time, right? I can see why you wanted to keep the denominator the same, Mark, because we never changed it until now, right? But anytime you have a conditional probability, you are kind of reducing your universe, right? You're reducing your universe to the universes where yeah, that has happened. But now we want to be careful here too. So before, the other question is what should go in the numerator? 100, say that again? Well, we would think so, but not that either, but you're close. You both. It is 90. So let's think about this. Oh, me do? All right, tell the class. I think, okay, yeah, no, let me give you some. So what I think Mars was trying to say, right? Because you did to see it, it's hard to verbalize it. So he's looking at the days that it's raining and cloudy. Now, why is he doing that? So we know it's given that it's cloudy. So we're living in this yellow this bubble, right? If we're in this bubble, these 90 days where it's raining and cloudy are the only rainy days we need to worry about, because these 22 are outside of the bubble, right? So they're not, if it is cloudy, these 22 days are not a possibility, right? So it's only the 90. That's obviously 0.5. Now notice the probability, and we see this is what we would expect, right? Notice P of A and P, A given B, are they the same in this case? No, one's 31%, the other one's 50%. So these events are, what do we call? These dependent or independent? Dependent, because the occurrence of B affected A. As we would expect, right? Everyone knows this, right? I'm just putting some mathematical language to it here, right? Of the days that it's cloudy, it rains 50% of the time. Just rains in general 31% of the time. That makes sense. I mean, the order of those, this climate data is a little off, but like, all right. Now, this one, do we think this is going to give us the same thing? Is B given A going to be the same as A given B? No, because now things are a little bit different. So before, we were living in that yellow circle. Now let's do orange. Okay, so what's the given event here? So B is cloudy. So this is cloudy if it rains. So we know not that it's cloudy in this case we know that it rained, right? So instead of knowing that, we can't say I'm absolutely in that circle on the left, now I am on the circle on the right. Or sorry. I know my math better than my direction, apparently. Or this might just be, this is my third 2-hour class today. So yeah. So what is going to change? Are we going to have, so what's our denominator going to be now? And what's our numerator going to be? It's 90, right? So notice that's the same in both of these problems. And that is 0.8. So that even makes, so notice these numbers are different, right? And this kind of makes sense. Like my intuition for this is that clouds typically cause rain, right? So sometimes you can have clouds without rain. Half the time you do. It's much harder to have rain without clouds, right? So that's why that's 8. Yeah, question.
So I know there's like a lot of different formulas that you can use to find the probability. So how do you know which one?
Okay, so there's 2 answers to that. So the first answer is you get used to it and you get a sense of it. Not what you want to get, but here's what you can do, right? You're going to have some problem, right? Let me give an example. Yeah. So here's an example, right? We had a scenario. You read the problem, you decide what the 2 events are, and then you translate each sentence to mathematical notation. Right? There'll be 2 or 3 or however many given probabilities, and there'll be this one that's unknown. You have to find the formula that contains all 3 probabilities, right? Because you have to use the one, right? If you have a formula that has however many like let's say that there are 10 quantities in a formula. If you know 9 of them, you can find the 10th one, right? So once you look at like what sort of information you're given, that tells you the formula, right? So for example, a formula that would have, so I'm trying to find F and 1 through 4 in here. There's a formula that would say F, probability of F plus probability of 1 through 4 minus probability and equals the probability of or. That wouldn't be a good one to use because I don't have that information, right?
That's the first formula that we talked about when we walked into the class?
Yes.
Okay.
Like that formula is true in this scenario, but it wouldn't be helpful because I'm missing a ton of the pieces in it, right?
Okay.
So it's both of those answers I said, right? You will use the formula that has all but one piece of information present so you can find the missing piece. Now, guessing which one that is takes some time, but while you're trying to figure that out, it'd be good to have them all written down in a place so you can be like, ooh, I know this, I know that. Ooh, I know 5 of the, there aren't any that have 6 in it, thank God, right? But I know 5 of the 6 pieces, so I can find the 6th piece. Or I know 2 of the 3, so I can find the 3rd. That's usually what it is, 2 of the 3, or the one that I gave today would have been 3 of the 4, right? Okay. Now let's use this to discover our formula. So notice, how could I write this probability, A given B? Notice, probability of A given B was, look at all the days in the universe of B, right? And then divide that by the number of days that are in both B and A. A and B divided by the number of days in B, correct? Now, maybe you've done this in algebra class, right? If you want to add, say, one half to 1/3, right? What's the technique you use to add these two fractions together? You need to get what? A common. And the way you do that is you like multiply. You've multiplied by forms, and you're allowed to do this because those fractions are equal to 1 when they're reduced, correct? I'm not going to do that here, and I'm not really going to enforce that, but this is going to inform what I'm doing here. So you don't have any idea why I'm doing this yet, but you'll just agree that this is valid. I could multiply the top and bottom of these fractions by 1/365. Of course, you have no idea why I'm doing that right now, but you will see in a second. Then I would have 90/365 over 180/365. Now, I'm not trying to get a common denominator because here I'm not trying to solve something like that. I'm trying to create a formula, right? Notice 90/365 is the probability of what? And 180/365 is, so we just discovered the formula for A given B. Probability of A given B is equal to the probability of A and B and you can get that by looking at this diagram, right? If I want to find the probability of A given B, I am restricting, right? Anywhere in the diagram is 100%, right? Or 1 out of 1, whatever. There is some restriction, right? The amount of, I'm only inside of, my whole universe is B, right? That's my bubble, as Mark said. So I'm living in that bubble, right? Find the probability I get into that bubble, right? What portion of this bubble of the B bubble has A occurred? Well, it has to be the part that's in both of them. So that's why that's the numerator, right? 90 ways out of 180. Now, it's not always, when it's numbers, like specific number of days, the intuition's easy, but I could just give probabilities, right? Since the probabilities is just that multiplied by a fraction, you can use this. So this is, Regina's asking about all the formulas. So this formula is probably one of the very important ones to memorize, right? And actually the multiplication formula I gave you guys earlier and this formula are the same thing. You can put a pin in that, I will come back to it, right? So this is, I say, the most important. So other than that, that formula we talked about at the beginning of class, memorize that formula and this formula, you're pretty good to getting things done. Those are the two formulas I'd expect you to memorize. Let me give you some other intuition here. So to generalize this, right, suppose that event F has M ways that it can occur. K of those ways also involve E occurring. Well, the probability of E occurring would be K out of M. I can multiply the top and bottom of this fraction by 1. You don't need to know the derivation of this, guys, right? Like you just need to know the formula and be able to use it. I just want to give you some sense of where it's coming from. Otherwise, you don't really know what the hell is going on, right? You're just being jerked around from formula to formula. And then, right, so K over N, right? If there are N total things in this whole square, that would be the probability of, there are K elements here, there are N total. That's the probability of E and F. And then M is the number of elements in F. There's a lot going on here, but really, all you have to memorize is this. And to help you with the structure, notice this F, this vent on the bottom, the vent to the right is also the event on the bottom. You divide by the probability of F, because that is the unit, that's like, remember, like that's what Marx called the bubble. That's the bubble you're living in. So you need to account for the size of that bubble. So this is the intuition for it. Notice, this is the correct formula I want you to memorize, but notice if I multiply both sides by the probability of F, these would cancel out. I would get probability of F times the probability of E given F is the probability of E and F. This again, you don't have to know, but it can help you. Notice that is the same formula here. So those two multiplication formulas I told you and this division formula are actually the same formula. One's just written as a multiplication fact, and one's written as a division fact. So you don't have to memorize. You memorize the formula I just taught you, you can just rewrite it. Right? This formula is telling you 2 times 3 is 6. This one's telling you 6 divided by 2 is 3. We'll do more examples later. So that's nice. Now we just need to use these formulas and we can figure this out, right? And this will help answer Regina's question. How do we know what formula to use? Right? And you need to be able to use the formulas, right? Like there's intuition for the rain and the cloudy story, right? Here, we don't even know what events E and F are, so there's no intuition you can use. You just have to use the math. All right, so we just learned this formula and you need to memorize it. It should be burned into your mind. Probability of E given F is equal to the probability of, we just learned it. Yes. All right, we'd be quickly done with this problem, except for something is not quite, what's our issue here? There's an issue. So if I have these two quantities, I can easily find out E given F. But there is an issue. What's the issue? Something's wrong. Why can't I just start plugging in numbers and getting my correct answer? I think what you're saying is we don't have the and. This is still not known. We know we have part of this. This is 0.5, but this over here is still a question mark, right? And instead we have something else. We have the or, but we want the and, right? Luckily, there's a formula that relates. What's the other formula that we learned? Can't multiply because that would, a lot of students want to do that. Multiplying assumes independence. We don't know that they're independent yet. We'll end up finding that they're independent, but you don't know that. So I could create another problem. What is the relationship between the or and the and? I gave you a form. It's the formula we mentioned at the beginning of class. Or F. Okay, so this is a two-step problem, right? We had one formula and we were like, sweet, but we're missing a part. Now notice, right? This is what I was telling you, right? Regina, you asked, how do I know what formula to use? Well, notice in this case, this is what we want, right? And we know the other three parts of this formula. There are four parts to this formula. You know three of them, right? That's enough to find the missing part, right? For any formula, if I say x plus y equals z, and I know z, that's not enough to give us x and y, right? But if you know all but one part, you can find the last part. So you just this is just simple algebra. I can do this. So I add the 0.4 and the 0.5, I get 0.9. But this side's 0.7. So what must I be taking away here? 0.9 minus something equals 0.7. Okay, if you're not seeing it, that's okay. That's a subtraction. What if it was 9 and okay, let's just isolate it. What if I want to isolate this, I need to subtract or 0.9, right? So I would have negative 0.2, which would be a problem if that was my final answer, right? But it's not because these 0.9s cancel out and I'm left with negative. Or multiply by negative, same thing in this case, right? And remember, when you multiply by a negative or divide by a negative, you're divided by -1, same thing. Absolutely. That gets me that 0.2 is E and F. You may have been able to solve that from here. If you just said 9 take away what is 7, the what has to be 2. So in this case, 0.2. Now that I have E and F, I can put that in here. And get 0.4. Notice something. So that's kind of these things, right? You have to use whatever formula relates the missing quantities to what's unknown. In this case, it was 2 steps. Notice here, P of E given F is 0.4. Something else important, 0.4 here? Yes. Notice E, the probability of E given F is the same as the probability of E in general. So what can we say about E and F? There you go. That was not a question here, but you could conclude that. Because event F did not make the event F's occurrence did not make the event E's occurrence more or less likely. So they must be independent. And because of that, Marge, you would have been okay doing what you did, but you would have been lucky because you were assuming independence until you had knowledge of it, right? And I could just as easily given you a problem where they were not. I'm going to do just one quick problem in a table, just so you can use to a table type problem. All right, so here's stocks. I'm sure you're going to learn about stocks and that stuff. If you do, tell me about it. I don't know how they work. All right, so event A is a stock. So here's a table, right? Price is on one dimension, yield is on the other. Does anyone understand how to read this table? We can just do one of these, right? Event A is that a stock has a yield of 2% or more. And we want an event C is that the stock price was from 0 to 50 bucks. We want to find the probability of C given A. There are 2 ways to do this. The intuitive way and then the formula, right? So let me just give you both of these. All right, so in this probability, in this C given A, which event do we know occurred, C or A?
C.
C. So we know that the stock price is 0 to $50. Just like in the Venn diagram, that restricted us to just part of the Venn diagram. In this case, that restricts us to just part of the table. What part of the table are we restricted to? We know that the price is from 0 to 50, so we must be in the top row. Does everyone follow what I'm saying? So since I'm in the top row, what must be the denominator of my fraction? 158. What must be now I want to know what's the percent that has a yield of 2 or more? Of those 158, how many have a yield of 2 or more? That's it. That's all you have to do to read this. Let me use the formula method. So the formula would say, it's going to end us getting us the same answer. Probability of A given C is equal to the probability of, so remember the top part of the formula for conditional is the and, right? I want you to have this formula memorized quickly. And on the bottom, is it probability of A or probability of C? Okay, so we can calculate this. So A and C is Well, there are 68 stocks that have both a high yield and a low price. Everyone see that? And if I want to find the probability of selecting that stock, how many total stocks are there? Right? Because this doesn't say given, I'm not restricted to that row anymore. Now I can say, now the probability of C is that I choose any stock that has that price, of which there are 158 out of 505. These numbers in the fraction cancel, and you will get the same answer. So I think when you have a table like this, the intuitive approach is easier, but you can also use the formula and it helps verify. I mean, we don't need to verify it. People found that out for a while, but it's good to verify it to yourself. How it works, what's the intuition there.